This is MEI Statistics Minor, Discrete Random Variables 2, the Poisson distribution. 2.1, the Poisson distribution as a model. Many situations occur in which we observe the count of events within a set unit of time, area, volume, length, etc. There are a few examples here. I'm just going to highlight a couple. So the number of births per hour during a given day. We are observing the count of the number of births within a set unit of time per hour. The number of cases is what we are counting of a disease in a different town. That is our set unit. The Poisson distribution is a discrete probability distribution specifically designed for the counting of these events that occur randomly in a given interval of time, or space. It was first proposed by the French mathematician Simeon Poisson, hence its name. Now, a discrete random variable with this probability function for values of x from 0 upwards, where lambda can take any positive value, follows a Poisson distribution with parameter lambda. In short, x is distributed as a Poisson distribution. With parameter lambda. Now, some of you may not have seen this letter here, E, and what it means in mathematics. Rest assured you will do soon, and you'll start to realise just how important it is. I'd say it's probably even more important than pi, which is another very famous constant. It is approximately 2.71828 blah 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 blah, and so it goes on. It goes on forever just like pi does. Okay. But there is a function on your calculator which is e to the power of. You can also use it as a constant. Now, what is the shape of the Poisson distribution? So if we have a look at it in GeoGebra, as you can see, we've got the Poisson distribution selected here. Here they have called it mu. It's generally called lambda, but that's what GeoGebra prefers to do it with. And you can see when the value of lambda is equal to 1, we've got our modal values up here, right at 0 and 1, and then it slowly goes downwards, and then it's got a very long right-hand tail that actually goes on forever. If I move it up to 2, you can see that the mode moves away from 0 and goes to 1 and 2. And it's a little bit more symmetric, but not a lot. If I go up to 5, there we see we've got a tail both ends now. Move up to 10, and you can see it's coming ever more symmetrical. In fact, it's actually starting to look a bit like the binomial distribution. Put it up to 15, and there we go. Starting to look even like the normal distribution. So, if x is representing the number of occurrences per interval of time or space, then x can be modelled by a Poisson distribution provided the following assumptions hold. Events occur at random. Events occur independently of each other, so the fact that one event has just happened doesn't make the next event any more or less likely. The average number of events in the given interval, and the average number is lambda, is fixed and finite. And this rate is proportional to the interval. So if we have a period of time twice as long, then the average rate, lambda, will be doubled. If it's halved, it will be halved. So this rate is proportional to the interval. And finally, events occur singly, so we don't have two things happening at exactly the same time. They happen one at a time. Some good examples of some things that may be distributed with the Poisson distribution: the number of phone calls on a randomly chosen day, insurance claims made by motorists in a given amount of time, particles emitted by a radioactive source in a given amount of time. A few more examples also appearing down there. Now, I did say may be distributed that way. There are a few things that we need to consider. For instance, this first question here, number of phone calls on a randomly chosen day. I would say, is it in an office? If so, I would suggest that Sunday versus Monday, there would not be a constant rate between the two. So you might need to restrict your days to Monday through Friday, or you may need to just consider Mondays. Insurance claims made by motorists in a given amount of time. Well, I would say that entirely depends on whether the insurance claim rate is constant, and I would be worried about questions in winter, because what about all the ice? Surely the driving conditions are worse in winter, you're going to have more accidents. And each other one will have questions that you may need to consider as to whether your assumptions are likely to hold or whether they're not. So in the next video we're going to be actually working out some of the probabilities for the Poisson distribution.